let's talk about some of these tricky situations that can arise with inverse trig. So I'm not going to write down the cheat sheet or anything today, our reference sheet, since maybe we'll just write that down as we go. But write it down if you want, and I'll see if we can get this camera to focus. Let me write a little bit more here. So let's start off with some things that you might see. Let's just start off with an easy one. So simplify sine of arc cosine of 3x. We specify that x is between 0 and a third. So we were working on this type of stuff on Wednesday. And remember, this is our ratio. Input of an inverse trig is a ratio. And then the output, once we compute that answer, is an angle. Let's just call it, something. Let's call it theta. And then we want to compute sine of this angle. So one key thing that they give us is that x is between 0 and 1/3. And we have this scaling factor of 3 here. So this 1/3 is important because when I multiply any of these x values by 3, that means the value that we're ultimately going to evaluate arc cosine on is going to be between 0 and 1. So what does that tell us? It tells us that the ratio is positive and we're using arc cosine, so quadrant 1. And actually, if the ratio is positive that we are inputting into an inverse trig function, it's always quadrant 1. So we can draw our triangle in quadrant 1, and we need this angle to have a cosine ratio of 3x. So we fill in our sides, 3x over 1, adjacent over the hypotenuse is our cosine ratio. We find the third side by the Pythagorean theorem. Remember to square both of those terms. So that's going to be a 9x squared plus y squared equals 1. Y squared is 1 minus 9x squared. And so y squared of 1 minus 9x squared. Do we need the plus or minus? In this situation, it's going to be dictated by what quadrant we're in. So our y was our vertical distance, and since it's in quadrant 1, it's going to be positive. It's going to be along the positive vertical axis. So we have our y, and then now all we want to do is compute sine of that. And that's our answer. Now, some tricky things that we can throw at you. Evaluates arcsine of pi. Careful with this guy, because what should this be? Remember, pi is just a number. And it's a number that it can be used in different situations. In this case, we are evaluating an inverse trig function, meaning that the ratio is pi. And we're supposed to have some angle whose sine ratio is pi. Well, what would that look like? If we were to try to draw this triangle, the angle should be such that one side is pi and the hypotenuse is 1. Is this possible? Remember, the hypotenuse should always be the biggest side, but yet pi is about 3.14. here we have a side length that's bigger than the hypotenuse, so it's not possible. Likewise, we talked about the domain and range for these guys. The domain for arcsine is minus 1 to 1. So pi is not in the domain. Meaning that this expression is undefined. So trick question with that one. Other things we need to be careful of is what happens when we evaluate an inverse trig and a trig function that are the same, that are supposed to be inverses of each other. So what's going to happen if we try to compute cosine of arc cosine of, let's pick any ratio, it doesn't matter. Let's pick something non-standard. Let's say 7/12. So how would we do this one? When we want to simplify something like this, just like we did in the first example, the ratio is positive. So the angle is going to be in quadrant 1. With a cosine ratio of 7/12. And then when I evaluate cosine on that, what are we going to get? That same ratio. Likewise, this actually isn't going to matter what we plug in there. Even if I just have an x, no matter what quadrant the angle is in, so remember arc cosine, it's going to spit out angles either in the first quadrant or the second quadrant. And if the cosine ratio is x, and then I'm asked to compute the cosine ratio, what are we going to get? We will always get back the argument. This is, in some sense, what we wanted, right? Remember, we cook up these inverse functions so that they undo the operations of the regular function, and vice versa. So if I do an inverse operation and then do that straightforward operation, so inverse cosine, then cosine, we should get back the number we started with in the input. And this is going to be true for all trig functions. So sine of arcsine of anything, whatever we want to put in there, as long as that's in the domain. So mind that, as long as x is between -1 and 1, we are going to get back the same thing. However, we got to be careful in the reciprocal case when we flip those two. So that's a rule. You guys can remember this one, but be careful because when we switch these two, it could change. So warning. Not necessarily true. If inverse trig comes first in the composition. Meaning if I have sine inverse of sine, we got to be careful. So let's take a look and see what can happen. Sorry, did everyone write all that? Cool. So let's evaluate inverse sine of sine of 4 pi over 3. And the problem that's going to come about is, how did we cook up these inverse functions? We had to first restrict the domain of the original functions. We had to restrict the domain of sine to what values? To minus pi over 2 to pi over 2. If the value is within that range, then the operations will undo each other. But if it's not, we're going to get a different answer. So 4 pi over 3 is not in minus pi over 2 to pi over 2. Meaning this sine function, while still having the same properties of sine, is not how we created this inverse sine, because the domain of this function is bigger than what we needed. It's too big for what we need, actually. So how do we evaluate something like this? Well, sine of 4 pi over 3, we know how to evaluate. So 4 pi over 3 is 3 pi over 3 plus 1 more pi over 3. And so our ratio is 1, 2, and square root of 3. The square root of 3 is going to be negative since we're in the negative y direction. The 1 is also going to be negative. And so now when we simplify this, we're going to have arc sine of, okay, sine of 4 pi over 3 is going to be minus square root of 3 over 2. But what happens when we evaluate arc sine of this? You have a negative ratio. And this needed to be the domain of our inverse trig, or our sine. It is necessarily the range of our inverse trig. Remember, so arc sine will always spit out values between minus pi over 2 to pi over 2. So the angle is in quadrant 4. Minus pi over 2 to 0. So our answer for this guy is, now we need a pi over 3. The reference angle is still going to remain the same. The reference angle for that guy was pi over 3. So our reference angle, it's always going to be pi over 3. It's just going to change quadrants if the original angle wasn't in the first or fourth, if it wasn't between minus pi over 2 to pi over 2. And so since it's a reference angle of pi over 3 and it's negative in the negative direction, we will have that arc sine of negative square root of 3 over 2 is negative pi over 3. Sorry, so let me rewrite that. So in summary, our inverse sine of 4 pi over 3, they don't cancel. These functions do not undo each other because this guy was not in the correct domain. And so it's actually going to change to minus pi over 3. Any questions on that? So always be careful if the inverse function, if you see the inverse function first in a composition, be mindful that the quadrants can change. And they can, even if we change trig functions, arc sine of sine, or excuse me, arc sine of cosine, there can still be this weird quadrant switching going on. Let's do one more in terms of finding the domain and range. And let's find the domain and range of 5 times arc cosine of 3x plus 2 minus 6. So how do we do this? The domain of cosine, inverse cosine, domain of inverse cosine of, let's pick a new variable, let's say z, is minus 1 to 1, right? Well, these are the cosine ratios we can input, which means whatever net results in the expression inside of an inverse cosine has to be between minus 1 and 1. So if we're given this function here with an expression like 3x plus 2 inside of an arc cosine, that 3x plus 2 has to be between minus 1 and 1. So if you remember way back, like in the first week, when we were doing absolute value inequalities, sometimes we have these compound inequalities. We can treat them as two separate inequalities if you want. Minus 1 is less than or equal to this, and then get another one, 3x plus 2 is less than or equal to 1. Or you can solve them both simultaneously. You would just perform all the operations to every piece. So in between each inequality. So let's subtract 2 from everything. Well, if minus 3 less than or equal to 3x is less than or equal to minus 1, and then I divide everything by 3. So we'll get minus 1 is less than or equal to x is less than or equal to negative 1/3. And this is what determined our domain. The range is a little different, and I think the range is a little tricky for some of you guys because the range, sometimes it's not as straightforward of a problem-solving process. You have to kind of just intuit what's going on. We want to look at the y-axis transformations. From whatever the parent function is. So let's say our parent function is just inverse cosine x. So our range, what are the outputs for inverse cosine? 0 to pi, quadrants 1 and 2. And now we have to ask, what transformations am I applying from this function to get this one? And in particular, what are the y transformations? So all of these, this 3x plus 2, remember, those are affecting the x-axis. The 3x is going to compress things. That plus 2 is going to shift things. It's this 5 and 6 that are going to change the y range. So we scale by 5. So in other words, we're doing 5. You can think of it as 5 times this range. In other words, if we have this 0 to pi, and I'm taking these numbers and multiplying them by 5. So 5 times 0 is 0, and then 5 times pi will go up to 5 pi. Let's put a bullet there. So that's the first step, scale by 5. And then what do? We subtract 6. So graphically, now we're at 0 to 5 pi. And now I'm taking all of these values, and when we subtract 6, we're just shifting them all downward. So we will have negative 6 to 5 pi minus 6. And 5 pi minus 6 is what it is. Remember, pi is a number. Unfortunately, it doesn't have a nicer expression like that. Than that. We can't get a decimal or anything for it without calculators. So that's how we leave it. So that's our range. Any questions? Cool. So that is it for today.